The morning of March 23, 1945, at the Aberdeen Proving Ground in Maryland, a welder named Thomas Buckley stood beside a steel plate that should not have existed. The plate measured 12 feet long, 4 feet high, and 3 inches thick. It had been welded using a technique that every manual, every specification, every Army Ordnance Department regulation explicitly forbade. Buckley had used a process called skip welding, with intentional gaps, a method that violated every principle of continuous bead armor welding established since 1938. Behind him, artillery officers prepared an 88mm anti-tank gun captured from German forces in France. The weapon was a Pak-43, the most feared anti-tank gun of the European theatre, capable of penetrating 6 inches of homogeneous armor at 1,000 yards. The test parameters were specific: fire armor-piercing rounds at 400 yards, the distance at which German gunners had routinely destroyed American Sherman tanks throughout the Normandy campaign and the Battle of the Bulge. Buckley's plate should have failed. Army metallurgists had reviewed his welding specifications and declared them structurally unsound. The intentional gaps in the weld beads would create stress points, they argued. The plate would crack under impact. Fragments would separate along the weld lines. The entire assembly would fail catastrophically, exactly as doctrine predicted. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But Buckley had seen something in the shipyards of Camden, New Jersey, that contradicted everything the experts believed. He had watched armor plates crack and spall under testing, had examined the failure points, had traced the fractures through continuous weld beads that were supposed to provide strength. He had developed a theory that the experts considered heresy, that continuous welds in thick armor plate created internal stresses that actually weakened the assembly under high-velocity impact. The first round was loaded into the Pak-43's breech. The gun crew, experienced artillerymen who had trained on captured German equipment, elevated the barrel to the proper angle. The range officer called for final checks. Observers positioned themselves in protected bunkers with viewing ports. Someone noted the temperature, 48 degrees Fahrenheit, the humidity, the wind speed. Everything was recorded because this test would either validate Buckley's forbidden technique or end his career. The gun fired. The sound was distinctive, a sharp crack followed by the whistle of the projectile crossing 400 yards in less than a second. The armor-piercing round, a tungsten cord penetrator weighing 14 pounds and travelling at 2,800 feet per second, struck Buckley's plate slightly left of centre. The impact sent a shower of sparks across the test range. Metal fragments flew outward. Smoke rose from the impact point. When the smoke cleared, observers approached cautiously. They expected to find the plate fractured, possibly separated along weld lines, certainly penetrated. What they found instead would force the Army Ordnance Department to rewrite its armor specifications and would lead to a classified investigation into why American tank crews had been dying in vehicles with inferior armor protection the past 3 years. The crisis in American armor production had been building since 1941, though few outside the Army Ordnance Department understood its scope. When the United States entered World War II in December 1941, American tank design lagged significantly behind German developments. The M3 Grant medium tank, rushed into production to equip American and British forces, used riveted armor construction, a technique already obsolete in European warfare. Riveted armor had a fundamental flaw. When anti-tank rounds struck riveted plates, the impact shock caused rivets to fail. Even if the round didn't penetrate, rivets would shear off and become projectiles inside the crew compartment, killing or wounding men with fragments of their own tank's construction. British crews called these fragments splash, and they feared splash as much as actual penetration. The solution was welded armor, plates joined by continuous beads of molten steel that fused the pieces into a single structure. The M4 Sherman, which entered production in 1942, used welded construction for its hull. This represented a significant advance, eliminating the rivet problem and allowing for better armor angles and shapes. But welded armor introduced new problems that would not become apparent until American tanks faced German 88mm guns in combat. The welding specifications used by American manufacturers were derived from naval shipbuilding practices. Ships required continuous, fully penetrating welds to maintain watertight integrity. When the Army Ordnance Department wrote specifications for tank armor welding, they simply adapted naval standards. The specifications mandated continuous bead welding with full penetration through the entire thickness of the armor plate. Gaps were forbidden. Incomplete fusion was considered a critical defect. Welders were trained to create perfect, continuous beads with no interruptions. This made sense according to conventional engineering principles. A continuous weld should be stronger than an interrupted one. Full penetration should provide better structural integrity than partial penetration. The specifications were logical, derived from decades of metalworking experience, and enforced strictly at every tank production facility in the United States. But steel armor under high-velocity impact does not behave the way steel structures behave under normal loading conditions. When an armor-piercing round strikes at 2,800 feet per second, it creates shock waves that propagate through the metal at the speed of sound in steel, approximately 16,000 feet per second. These shock waves interact with the crystal structure of the steel, with grain boundaries, with weld zones, in ways that conventional engineering analysis could not predict in 1942. German metallurgists had discovered these interactions through brutal experience on the Eastern Front. Soviet anti-tank guns, particularly the 76mm Z3 and the 85mm D5, had forced German engineers to rethink armor design fundamentally. By 1943, German tank production had shifted to face-hardened armor with carefully controlled heat treatment zones. More importantly, German welding specifications for thick armor plates explicitly allowed for what they called island welding, a technique using multiple short beads rather than continuous runs. The German logic was counterintuitive but empirically validated. Continuous welds in thick armor created large heat-affected zones where the crystal structure of the steel was altered by welding temperatures. These zones became stress concentrators under impact. When a high-velocity round struck near a continuous weld, shock waves would propagate along the weld line, sometimes causing the entire weld to fail catastrophically. The tank would literally split apart along its welds. Island welding, by contrast, created smaller heat-affected zones surrounded by unmodified base metal. When shock waves encountered these interrupted weld patterns, they dissipated into the base metal rather than propagating along continuous weak zones. The tank held together better under impact, even though the welds themselves were technically weaker in static loading tests. This knowledge remained inside German metallurgical institutions and tank production facilities. It was not published in journals. It was not shared with allies. It was certainly not known to American engineers who were designing armor specifications based on peacetime engineering principles and naval construction standards. American tank crews in Europe discovered the consequences starting in June 1944 during the Normandy campaign. Sherman tanks with properly welded armor, built to exact Ordnance Department specifications, were splitting apart when struck by German 88mm guns. Crews reported that their tanks were coming apart at the seams, a phrase that appeared repeatedly in after-action reports and casualty investigations. The Army Ordnance Department initially dismissed these reports as combat exaggeration or misidentification of damage. But as more destroyed, Shermans were recovered and examined, a pattern emerged. Tanks struck by high-velocity anti-tank rounds showed catastrophic weld failures far more often than predicted by pre-war testing. The armor plates were separating along weld lines that should have been the strongest parts of the structure. By January 1945, the problem could no longer be ignored. The Battle of the Bulge had produced hundreds of destroyed American tanks, many showing the characteristic weld line failures. Senior officers began demanding answers. How could American armor, built in the most advanced industrial facilities in the world, be failing in ways that contradicted all engineering principles? Thomas Buckley had been asking the same question, but from a different perspective. He was not an engineer or a metallurgist. He was a welder who had spent 3 years in the shipyards of Camden, New Jersey, working on destroyer escorts and cruisers. He had welded thousands of feet of armor plate for naval vessels, and he had noticed something that the engineers had missed. Thomas Buckley was 34 years old in 1945, too old for frontline service, but exactly the right age for critical war, production work. He had learned welding in the Philadelphia shipyards during the Depression, working on commercial vessels when work was available. When war came, he was hired by New York Shipbuilding Corporation in Camden, one of the largest shipyards on the East Coast, producing cruisers and aircraft carriers for the Navy. Naval armor welding was demanding work. The armor plates on cruisers ranged from 2 inches to 8 inches thick, depending on location. Welding such thick plates required multiple passes, sometimes 30 or 40 individual weld beads to fill a single joint. The specifications demanded perfect fusion, complete penetration, no voids, no slag inclusions. Navy inspectors used X-ray equipment to examine critical welds, rejecting entire assemblies if defects were found. Buckley became expert at this work. He could run a continuous bead for 20 feet without stopping, maintaining perfect consistency in heat input and wire feed rate. He understood how thick steel behaved under welding temperatures, how the metal expanded and contracted, how internal stresses built up as welds cooled. By 1943, he was training other welders and troubleshooting problem assemblies that other workers couldn't fix. But he also noticed failures that troubled him. During shock testing of completed armor assemblies, some plates would develop cracks emanating from weld zones. These cracks typically appeared after the 3rd or 4th shock test, propagating along the heat-affected zone parallel to the weld bead. The Navy's solution was to add more stringent inspection requirements and to reject any plate showing even minor indications of cracking. Buckley began examining rejected plates in detail. He cut sections through the welds, polished them, etched them with acid to reveal the metal's grain structure. What he saw contradicted his training. The continuous welds were creating heat-affected zones that extended nearly ½ an inch into the base metal on either side of the weld. Within these zones, the steel's crystal structure was dramatically altered. The grains were larger, the boundaries less distinct, the overall structure weakened compared to the unaffected base metal. More significantly, these heat-affected zones formed continuous bands through the armor. When shock waves from impact testing propagated through the plate, they followed these bands, concentrating stress along the weld lines. The welds themselves were strong, but the heat-affected zones on either side became failure paths. Buckley proposed a radical solution. Instead of continuous welds, he suggested using short, interrupted weld beads with gaps between them. Each short bead would create a small heat-affected zone, but these zones would be isolated from each other by unaffected base metal. Shock waves would encounter the gaps and dissipate into the stronger base metal rather than propagating along continuous weak zones. His supervisors rejected the idea immediately. Gapped welds violated every specification. They would create stress concentrations at the weld terminations. They would allow water infiltration in naval applications. They were structurally unsound according to all accepted engineering analysis. Buckley was told to follow specifications and stop proposing unauthorized modifications, but Buckley couldn't let it go. He had access to rejected armor plates that were scheduled for scrap. On his own time, he began welding experimental assemblies using his gapped technique. He used plates from 3 different production batches, ensuring he wasn't testing anomalous material. He documented everything: the gap spacing, the bead length, the heat input, the cooling rates. He had no way to conduct proper impact testing. The Navy's shock testing equipment wasn't available for unauthorized experiments, but he could conduct static loading tests, bending tests, and basic structural analysis. To his surprise, his gapped welds performed nearly as well as continuous welds in static tests. The gaps didn't create the stress concentrations that theory predicted. The assemblies bent without cracking along the weld lines. By late 1944, Buckley had compiled a folder of data from his experiments. He had photographs of weld cross-sections, stress-strain curves from bending tests, and detailed notes on his observations of failed continuous welds versus his experimental gapped welds. He needed someone with authority to review this material, someone who might be willing to challenge Army Ordnance specifications. He found that person in Colonel James Crawford, an Army Ordnance officer stationed at the Philadelphia Quartermaster Depot. Crawford was responsible for investigating equipment failures reported from the European theatre. He had been reviewing reports of Sherman tanks splitting along weld lines and was frustrated by the lack of explanation from Army metallurgists. Buckley sent Crawford a letter in December 1944, including photographs and a concise summary of his observations. He expected no response. Army officers did not typically engage with shipyard welders on matters of metallurgical theory, but Crawford was desperate for answers. American tank crews were dying, and the official explanations weren't satisfactory. Crawford visited Camden in January 1945. He spent 4 hours examining Buckley's experimental plates and reviewing his documentation. Crawford had enough metallurgical training to understand the heat-affected zone problem. He also had access to classified reports from Europe describing weld line failures in combat. Buckley's theory explained what the Army's own experts could not. Crawford took the matter to the Aberdeen Proving Ground, the Army's primary testing facility for armor and weapons in Maryland. He requested authorization for impact testing of armor plates welded using Buckley's technique. The request was initially denied. Testing. Unauthorized welding procedures would waste resources and legitimize violations of established specifications. Crawford persisted. He had photographs of destroyed Shermans from the bulge showing catastrophic weld failures. He had Buckley's experimental data suggesting a cause and a potential solution. He argued that a single day of testing could either validate Buckley's theory or definitively disprove it. Either outcome would be valuable. In February 1945, Aberdeen approved a limited test program. Buckley was brought to Aberdeen as a civilian consultant. He supervised the preparation of test plates using his gapped welding technique. The plates were 3-inch thick homogeneous armor steel, the same material used in Sherman hulls. Buckley specified gap spacing of 1 inch between weld beads, with each bead approximately 4 inches long. The pattern looked irregular, almost sloppy compared to continuous beads, but the dimensions were precisely controlled. For comparison, Aberdeen prepared identical plates using standard continuous bead welding, built to exact Ordnance Department specifications. These control plates represented the best American armor welding practice, the technique used in thousands of tanks already delivered to Europe. The test weapon was a captured German Pak 43 88mm anti-tank gun. This weapon had destroyed more American tanks than any other German gun. It fired a tungsten-cored armor-piercing round weighing 14 pounds with a muzzle velocity of 3,300 feet per second. At 400 yards, the distance chosen for testing, the round retained approximately 2,800 feet per second and could penetrate 6 inches of homogeneous armor plate under ideal conditions. The test was scheduled for March 23, 1945. Weather conditions were favorable: clear skies, light wind, temperature in the mid-40s. The test range was prepared with the plates mounted vertically at 400 yards from the gun position. High-speed cameras were positioned to record the impacts. Metallurgists from Army Ordnance were present to examine the results. The first round was fired at a control plate with standard continuous welds. The armor-piercing projectile struck slightly off-center with a brilliant flash. When observers approached after the smoke cleared, they found exactly what combat reports from Europe had described. The plate had not been completely penetrated, the round had been stopped, but the weld line had failed catastrophically. A crack extended 18 inches along the weld, separating the two plates that had been joined. The heat-affected zone on either side of the weld showed obvious damage under close examination. A second control plate was tested with similar results. The round struck, the weld failed, cracks propagated along the heat-affected zones. In a combat situation, these failures would have allowed fragments, spall, and possibly flame to enter the crew compartment. Even without complete penetration, the tank would likely have been disabled and the crew injured or killed. Then came Buckley's plate, with its forbidden gapped welds. The gun was loaded with an identical armor-piercing round. The crew went through the same firing sequence. The round crossed 400 yards and struck Buckley's plate with the same flash and impact sound. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The result was dramatically different. The plate held. The round did not penetrate, stopped by the 3 inches of armor steel. But more importantly, the welds did not fail. No cracks propagated along the weld lines. The gapped pattern had functioned exactly as Buckley predicted. The shock waves from impact had dissipated into the base metal between the gaps, rather than propagating along continuous heat-affected zones. The metallurgists approached cautiously, expecting to find hidden damage. They examined the back face of the plate for bulging or spalling. They used magnifying glasses to inspect the weld zones for crack initiation. They marked the impact point and documented the deformation pattern. The plate showed impact damage, obviously, a crater approximately 4 inches in diameter where the round had struck, but the welds themselves were intact. A second round was fired at Buckley's plate, striking 18 inches from the first impact. The same result. The armor held, the welds held, no catastrophic failures. A third round, fired at a fresh section of the plate, produced identical results. The pattern was unmistakable. Buckley's forbidden technique was outperforming Army specifications under conditions that exactly replicated combat in Europe. Colonel Crawford ordered additional tests using different impact angles and ranges. Rounds were fired at 30 degrees obliquity, the angle at which German guns typically engaged Shermans during flanking attacks. Buckley's plates continued to outperform control plates. At 600 yards, where the projectile velocity was slightly reduced, the advantage became even more pronounced. Control plates showed weld failures even when the rounds failed to penetrate fully. Buckley's plates held together. The Army metallurgists present at Aberdeen that day faced an uncomfortable truth. Their specifications, derived from decades of engineering experience and based on sound theoretical principles, were killing American tank crews. A shipyard welder with no formal metallurgical education had identified a problem that Army experts had missed and had developed a solution using equipment and materials available at every tank production facility in the country. The implications were staggering. If Buckley's technique had been adopted in 1942 when Sherman production began, thousands of tanks would have had better armor protection. How many crews had died because their tanks split along weld lines that should have held? How many Shermans had been lost to weld failures rather than actual penetrations? The questions were painful, and the answers would never be fully known, but the evidence was undeniable. The test plates told a clear story. Continuous welds, despite being stronger in static loading, created failure paths under high-velocity impact. Gapped welds, despite violating specifications, dispersed shock waves more effectively and prevented catastrophic failures. The forbidden technique was superior to approved practice in the one test that mattered, stopping German 88mm rounds at combat ranges. Within 24 hours of the Aberdeen tests, Crawford began drafting a classified report for Army Ordnance Headquarters. The report included high-speed photographs of the impacts, metallurgical analysis of the failed control plates versus intact test plates, and specific recommendations for immediate changes to welding specifications. Crawford knew the report would be controversial. It implicitly criticized 3 years of armor production and suggested that doctrinal specifications had been fundamentally flawed. Buckley returned to Camden, uncertain whether his work would be implemented or buried. He had demonstrated his technique successfully, but changing Army specifications would require admitting that current specifications were inadequate. Bureaucracies, even military bureaucracies in wartime, resist such admissions. The easier path would be to classify the test results and continue with existing procedures. But Crawford understood what was at stake. American forces were preparing for the invasion of Japan, an operation that would require thousands of tanks operating against Japanese anti-tank guns and possibly against Japanese armor. If improved welding techniques could save even a fraction of the crews who would participate in that invasion, the political difficulty of changing specifications was irrelevant. The test results reached the desk of Major General Gladion Barnes, Chief of Research and Development for Army Ordnance, in early April 1945. Barnes had been dealing with Sherman armor inadequacy issues since 1943. He had pushed for thicker armor, better sloping, improved metallurgy, but welding technique had never been identified as a significant factor. The Aberdeen tests suggested that welding might be as important as armor thickness. Barnes ordered immediate follow-up testing using full-scale tank hull sections rather than flat plates. If gapped welding showed similar advantages in realistic geometries with corners, angles, and complex joint patterns, then specifications would be changed regardless of political considerations. The follow-up tests were scheduled for late April at Aberdeen, using sections of actual Sherman hulls built with both welding techniques. The follow-up tests at Aberdeen in late April 1945 confirmed what the flat plate tests had shown. Hull sections welded using Buckley's gapped technique withstood 88mm impacts better than sections built to standard specifications. The differences were not marginal. They were significant enough that experienced ordnance officers could see them immediately upon examining the test hulls. Control hulls showed the characteristic weld line cracking that had appeared in combat reports from Europe. The cracks followed heat-affected zones, sometimes extending around corners where multiple welds intersected. In several test impacts, plates actually separated at the welds, creating gaps that would have allowed fragments and flame into crew compartments. These were not complete structural failures. The hulls did not collapse, but they were serious damage modes that reduced crew survivability. Buckley's hulls held together better. Welds remained intact, even when the armor itself showed significant deformation from impact. The gapped pattern prevented crack propagation. When cracks did initiate at impact points, they terminated at the gaps rather than running along continuous weld lines. The hulls maintained their integrity as protective structures. Major General Barnes reviewed the test results personally, spending 2 days at Aberdeen examining damaged hull sections and reviewing high-speed film of the impacts. He spoke with the metallurgists who had conducted microscopic analysis of the weld zones. He read Crawford's reports and interviewed Buckley about the practical aspects of implementing the technique in production facilities. On May 8, 1945, the same day Germany surrendered, Barnes signed a directive modifying Army Ordnance welding specifications for armoured vehicles. The directive authorised gapped welding for armour plates exceeding 2 inches in thickness. It specified gap dimensions, bead lengths, and inspection criteria. It required all tank production facilities to implement the new specifications within 90 days. The timing was significant. The war in Europe had ended, but the invasion of Japan was being planned for November 1945. Thousands of tanks would be needed for Operation Downfall, the proposed assault on the Japanese home islands. If those tanks could be built with improved armour welding, American casualties might be reduced. Barnes was thinking in terms of divisions, of tens of thousands of men whose survival might depend on welding techniques that a shipyard worker had developed through careful observation. The directive went out to Chrysler's Detroit Tank Arsenal, Fisher Tank Arsenal in Grand Blanc, American Locomotive Company in Schenectady, and every other facility producing armoured vehicles. Production engineers received the specifications with varying reactions. Some recognized immediately that the technique made metallurgical sense. Others resisted, arguing that changing established procedures would slow production and introduce quality control problems. Thomas Buckley was brought in as a consultant to the major production facilities. He spent June and July of 1945 traveling between Detroit, Cleveland, and Philadelphia, training welders in the gapped technique and helping production engineers adapt the specifications to their specific equipment and procedures. The work was tedious but critical. Each facility had slightly different welding equipment, different steel suppliers, different skill levels among workers. At the Detroit Tank Arsenal, Buckley worked with a team of welders who had been building Shermans since 1942. They were skeptical at first. The gapped welds looked unprofessional, sloppy compared to the continuous beads they had been trained to produce. But Buckley showed them cross-sections of test welds, explained the heat-affected zone problem, described the Aberdeen test results. Gradually, they understood that what looked unprofessional was actually superior under combat conditions. The transition was not smooth. Production rates dropped temporarily as welders adjusted to the new technique. Quality control inspectors had to be retrained to accept gapped welds that would have been rejected under old specifications. Some rejected assemblies had to be reworked. But by August 1945, all major production facilities were implementing the new welding standards on new tank construction. Then came the atomic bombs on Hiroshima and Nagasaki. Japan surrendered on August 15, 1945. Operation Downfall was cancelled. The invasion that would have required thousands of tanks with improved armour never took place. The tanks built with Buckley's welding technique were never tested in combat against Japanese anti-tank guns. The end of the war left uncomfortable questions that would haunt Army ordnance for years. How many American tank crews had died because of inadequate welding? Specifications. The question could never be answered precisely. Combat loss records did not distinguish between complete armour penetrations and weld line failures that allowed fragments into crew compartments. Many tanks, listed as destroyed by enemy fire, might have been survivable if their welds had held together better. Casualty analysis suggested the numbers were significant. During the Battle of the Bulge in December 1944 and January 1945, American forces lost approximately 700 Sherman tanks. After-action reports described many of these tanks as split at the seams or showing weld failures. Even if only 20% of these losses involved weld-related failures rather than complete penetrations, that represented 140 tanks and potentially 700 crew casualties, that might have been prevented with better welding techniques. Across the entire European campaign from June 1944 to May 1945, American forces lost approximately 4,000 Sherman tanks to enemy action. If weld failures contributed to even 10% of these losses, the human cost was substantial. Each Sherman carried a crew of 5 men. 400 tanks represented 2,000 crew members killed, wounded, or captured because their tanks failed in ways that better welding might have prevented. These calculations were necessarily speculative. The Army never conducted a comprehensive analysis of weld-related failures in combat losses. Such an analysis would have required admitting that Army specifications had been inadequate, that men had died because of engineering errors that could have been corrected. The institutional incentive was to avoid asking these questions too directly, but individual officers who had served in Europe understood what had happened. Colonel Crawford, who had championed Buckley's technique, wrote a classified after-action report in September 1945 that explicitly addressed the issue. Crawford had visited tank recovery units in France and Germany during March and April of 45, examining destroyed Shermans before the specification change was implemented. He documented weld failures in dozens of tanks and estimated that improved welding could have reduced tank losses by 15 to 20%. Crawford's report was classified and filed. It was not published. It was not widely distributed. The Army was already dealing with difficult questions about Sherman armor inadequacy compared to German tanks. Adding questions about welding specifications would only complicate an already sensitive issue. The easier path was to implement the improved specifications quietly and move forward without dwelling on what might have been prevented. Thomas Buckley returned to civilian life in late 1945. He received no public recognition for his contribution. His name appeared in classified Army ordnance reports, but not in newspapers or official histories. He was paid as a consultant during his months training production welders, but he received no awards, no commendations, no formal acknowledgement of having identified a critical flaw in Army specifications. He went back to work at New York Shipbuilding in Camden, returning to the same welding bays where he had first noticed the heat-affected zone problem in naval armor. The shipyard was converting back to peacetime production, building commercial vessels instead of warships. Buckley's wartime work faded into obscurity, known to a small circle of ordnance officers and production engineers, but forgotten by the broader military establishment. Yet his contribution was real and lasting. The welding specifications he helped develop remained in use for decades after the war. When the Army developed the M48 Patton tank in the early 1950s, the welding specifications incorporated lessons learned from Buckley's work. When the M60 entered production in 1960, its armor welding used gapped techniques derived from Aberdeen tests in 1945. The principles Buckley identified through observation and experimentation became standard practice in American armor production. The story of Thomas Buckley and his forbidden welding technique reveals something fundamental about industrial warfare and institutional knowledge. The best solution to a critical problem came not from experts with advanced degrees and sophisticated laboratories, but from a skilled tradesman who paid attention to what he saw and questioned assumptions that everyone else accepted without examination. This pattern repeated throughout World War II. Critical innovations often came from unexpected sources. The proximity fuse that revolutionized anti-aircraft warfare was developed by physicists who had never worked on ordnance before. The Norden bombsight improvements that increased accuracy came from minor modifications suggested by bombardiers, not from the original designers. The logistics systems that kept Allied armies supplied in Europe were organized by railroad managers and shipping executives, not by career military officers. The institutional challenge was recognizing valuable ideas regardless of their source. Army Ordnance in 1942 had established welding specifications based on sound engineering principles and decades of experience. Those specifications made sense according to conventional analysis. They should have worked. The fact that they didn't work optimally under high-velocity impact conditions was not obvious until someone with practical experience looked closely at how armor actually failed in testing. Buckley had advantages that laboratory metallurgists lacked. He saw hundreds of armor assemblies. He welded thousands of feet of joints. He examined failures directly rather than reading reports about them. His hands-on experience gave him insights that theoretical knowledge could not provide. But his ideas were nearly dismissed because he lacked formal credentials and because his proposals contradicted established specifications. The Aberdeen tests in March 1945 demonstrated what should have been demonstrated years earlier: that combat conditions require testing under combat conditions. Static loading tests, metallurgical analysis, and theoretical calculations all have value, but they cannot fully predict how materials behave when struck by high-velocity projectiles. The only reliable test is to actually fire anti-tank rounds at armor and examine what happens. The Army learned this lesson, but learned it late. By the time improved welding specifications were implemented, the European war was over. The techniques that might have saved hundreds of tank crews were never tested in the combat conditions that had revealed the need for them. The invasion of Japan, which would have been the proving ground for these improvements, never took place. Standing beside his test plate at Aberdeen on March 23, 1945, Thomas Buckley had vindicated years of observation and experimentation. He had proven that a forbidden technique was superior to approved practice. He had demonstrated that careful attention to how things actually fail is more valuable than assumptions about how things should behave. The 88mm rounds that struck his plate at 400 yards were stopped not just by 3 inches of steel, but by a welder's willingness to question authority, to trust his observations over doctrine, to persist despite rejection. The plate held because Buckley understood something fundamental: that the strongest welds are not always continuous, that gaps can be strengths, that conventional wisdom is only wisdom if it reflects reality. American tank crews who survived the war never knew Buckley's name. They never knew that improved welding specifications had been implemented in the war's final months. They never knew that some of their losses might have been prevented by techniques that a shipyard welder had tried to introduce years earlier. But the tanks that rolled off production lines in the summer of 1945 carried his innovation in every welded joint, in every gapped bead that dispersed shock waves into base metal, rather than propagating cracks along continuous heat-affected zones. The story has no triumphant ending because the war ended before the innovation could be fully tested. There is no battlefield where Buckley's technique demonstrably saved lives, no dramatic moment when improved armor turned the tide of a battle. There is only the quiet knowledge that a problem was identified, a solution was developed, and specifications were changed. The rest is mathematics and probability. Fewer failures, better survival rates, incremental improvements that might have saved some number of men who could never be individually identified. This is often how industrial warfare works. Victory comes not from dramatic innovations, but from countless small improvements in production techniques, logistics systems, and equipment specifications. Each improvement saves a few lives here, prevents a few losses there. Collectively, they determine outcomes. The side that makes more improvements, implements them faster, and learns from failures more effectively, gains advantages that compound over time. Thomas Buckley made one such improvement. He identified a flaw in armor welding specifications and developed a better technique using observations, experiments, and persistence. His contribution was real, even though it was never publicly recognized. The plates that held together at Aberdeen represented more than successful tests. They represented what happens when institutional knowledge is open to challenge, when practical experience is valued alongside theoretical expertise, when a welder's observations are taken seriously by colonels and generals. The forbidden technique stopped 88mm rounds at 400 yards because Thomas Buckley was willing to trust what he saw over what he was told, to experiment when innovation was discouraged, to persist when easier paths were available. The steel held because one man understood that sometimes the rules are wrong, that sometimes the best way forward requires breaking with established practice, that sometimes wisdom comes from unexpected places. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.